It's late. You've had a few drinks. There's no train expected. Nature's calling. What could possibly go wrong?
Where are we? We're here at the Golden Gate Railway Museum in San Francisco, and we're testing the myth about peeing on the third rail.
Oh, this is the one guy found himself late at night in a train yard, peed on the third rail, the electrified rail, got electrocuted and died?
That's the one.
Some subway systems are powered by an electrified rail on the track. A steel paddle slides along the top of that third rail, arcing as it draws current. There's enough power in the New York subway to light the whole state of Vermont. Rob Lobenstein is the superintendent of that system. He's well aware of this myth.
My first day on the job, they give you all the safety tips and the warnings, and that's the very first thing they tell you not to do.
Okay, so for those of you guys who've seen this, Mythbusters, peeing on the third rail, is it possible to get shot by pissing on something electrified?
No.
Does anybody remember their conclusion?
No.
Okay, so they will kill if you're saying no. You've seen the show?
Yeah.
I have not seen the show, but it kind of seems like the same concept as like pouring gas on a fire from a gas can, except human-wise. And I mean,
all right, so Caleb,
I haven't seen the show.
All right, Caleb, I'm going to give you just 5 points for venturing your guess. Matthew, you wanted to say something?
Yeah, they said that it wouldn't happen because it's not laminar enough flow, and there's too many.
All right, so what they basically they're saying that I'm going to give you 10 points for actually remembering it. This is actually used as a reference. They usually say that the urine stream would not be continuous enough to carry the current. That's what they're going to come up with. And then the next few people who tried it end up getting themselves killed. One person ended up pissing on the third rail here in Chicago, didn't survive. The other guy tried it in Brooklyn, New York, he didn't survive either. So the question is, what is it that Mythbusters end up missing on this one? So I love the show for obvious reasons. It's a really good show, but the less obvious reason is because sometimes they get it completely wrong because these guys are not physicists or engineers. In this one, they will get wrong completely. They will miss the point on this one. So the question is, where'd they go wrong? And they never, they couldn't figure out why the experiment didn't work out, as you will find out. All right. Let me see. Electrocution in China, we'll get back
This
to
little
it.
light burns all day and all night. It burns on its own internet site. It has lit the firehouse since the pumper was pulled by a horse.
Just gave enough light for the volunteer firefighters when they responded to the fire bell to come in, light their kerosene lanterns, get their equipment, and then go to the fire.
That was 1901, when no one could expect the bulb would shine for a century. The Livermore bulb has been turned off only twice when it was moved to new station housing. It has burned for 880,000 hours. The 4-watt bulb with early carbon filament was made by the Shelby Electric Company in Ohio. Look at it from below, and it seems to say it's on. Gary Drummond is an amateur local historian.
It's been one of those things in the community that's never been given. Oh, yeah, we've got a light bulb that's been burning for a long time down at the fire station.
This is the oldest burning bulb ever.
School children visit the light bulb. Either they, their parents, or grandparents were born when this light was first turned on. A visitor's book is filled with signatures from places like Japan and Ukraine. Today, the bulb hangs high out of the way, but it was not always treated with reverence. Fire Chief Gary Stewart says he comes to work every day hoping the bulb still works.
People would throw a Nerf ball or a Frisbee. It would occasionally swing on its cord. Some firefighters would come by and touch it to tap it for good luck. It was just the old bulb that was hanging around the house.
It isn't much to look at, and it doesn't cast much light, but it works.
And in a world that's just whirling with change, it's there, still, steady.
For those who ask why they can't make light bulbs like it today, the answer may lie in the fate of Shelby Electric, which went out of business. You can make light bulbs that last, but you won't last long making them. Brian Rooney, ABC News, Livermore, California.
All right, so I have a few questions to ask. Number one question is, why did the company go out of business, in your opinion?
I mean, they got a product that actually worked, and then they probably had trouble getting people to buy new ones.
Probably cost too much.
Yeah, probably.
All right, so I'm going to give you guys 5 points each. What's the real reason? Okay, so that's the reason that these guys were driving for, which is not true, obviously. All right, so if you got a degree in English and if you're writing news items for different outlets, that's what you write, I assume. But that shows lack of understanding. Why did the company go out of business?
So I'm thinking that other companies were like a bit jealous of them, and so like their light bulb like was able to last forever, and they decided like, how the hell are we going to sell anything if they have a light bulb that lasts hundreds of years? Like how could you? I mean, really? Yeah.
Okay. I'm going to give you 5 points for your conspiracy theory. All right. So let's focus on the physics of it. What's the purpose of a light bulb? Generate light. So you turn on the light and you can't see anything. So what do? Do you buy this light bulb?
No.
Or as opposed to getting a light bulb, which is going to last maybe 25,000 hours, but at least you can see what's going on, right? So what's the problem with this light bulb? It's not generating enough light, guys. That's what's the problem. I don't care that it's going to last a century. If I can't see, I'm not going to buy it. So eventually people said, screw this. All right. They ran out of business because it's not generating enough light. All right. Now that we had a heart-to-heart about the meaning of life, let's move on. What the hell am I looking at? All right, look at the filament, for God's sake. It's all over the place. All right. Why is the filament so long? Why did they make the filament so long? All right. So number one.
Maybe make it longer, you get more light out of it, probably.
Okay, that's not a bad theory. I'm going to give you 5 points for that one. Make it longer. Maybe you're going to get more light on it. Maybe that's what they're trying to do. What do we use if it's an incandescent light bulb? We use tungsten, right? All right, so back then they were using carbon, so that's a carbon filament. All right, what's the advantage of tungsten over carbon?
Lasts longer, cheaper, produces more light.
Okay, the most importantly, it produces more light, right? So why does tungsten produce more light than carbon? All right, so those are the things that we will get to investigate. Moving forward.
Direct contact with energized power lines or power equipment can kill you.
All right, this is a bit of a review because this is one of the concepts that we will have to focus on.
There's another type.
Remember the step potential?
Hazard just as deadly called step potential, like ripples on the surface of a pond. For a person walking towards an energized wire on the ground, or an object attached to or otherwise in contact with the ground, they are placing themselves in a potentially hazardous situation. As you walk toward the conductor, your leading leg will be in a higher potential ring of voltage than the leg behind it.
All right, so when there's a voltage potential
Because
difference, what happens? The charges go from higher voltage towards the lower voltage, right? So the charges will move from higher voltage towards the lower voltage.
Have 1 foot.
So potential difference is what drives the charges to move from a higher potential towards the lower potential.
But in one potential ring of voltage, and the other foot in a different potential ring of voltage, the electric current now passes through your body.
So voltage difference or potential difference is what drives the current. The current is the motion of charges.
And can injure or kill you. Therefore, keep your distance. Stay back at least 10 feet from any down power line or equipment. If you find yourself trapped in a vehicle that is in contact with a utility pole or a power line, stay inside the vehicle until someone from the power company tells you it is safe to get out. If there is an impending emergency, such as a fire, where you must leave your vehicle, there's...
All right, so we've seen this. So that's the concept that we're going to build upon. Right, those are... All right, so what's current and what drives current? Why am I... Did we skip something there? Okay. All right, so what is current?
An atom's nucleus has a positive charge. Electrons orbiting the nucleus have a negative charge. When electric current flows, electrons are torn from atoms and move freely.
Electricity is the flow of electrical charge, and most of the charge flows as electrons.
All right, electricity or electrical current is the flow of negative charges, electrons. All right, electrons moving in the same direction is known as current. The flow of electrons in the same direction is your current. Electrons are actually free to move within metals. They move at random directions. If you can get them to move in the same direction, that's known as current. So speaking of current, how do you get the electrons to move in the same direction?
Give them somewhere to go.
From the field, from being positive to negative.
Okay, who said that?
Positive to negative?
Okay, yeah, I like what you said. All right, give yourself 5 points for that one.
That was pretty insightful.
It's actually, everything that we said, we talked about so far is the background stuff that we will build on. Okay, so finally we're getting into the applications of it. So what do you have? The metals they got conduction electrons. They move at random directions, so the idea is to get them to move in the same direction. So if you can get them all to move in the same direction, if you make them flow in the same direction, this is known as current. So the question is, how do you get them to move in the same direction? The easiest way to do it is obviously you have to set up regions, opposite charge regions. One region is going to be negative charge, the other region is going to be positive charge. And then so what happens is going to set up an electric field inside. So there's going to be an electric field in this direction. An electric field acting on these charges will induce a force. So this charge will accelerate in the opposite direction of the electric field. That's it. All right, so notice that there's an electric field from left to right, and there's a separation distance between these two regions. Strength of the electric field in the separation distance is known as voltage or voltage difference. So that sets up a voltage difference immediately between these two opposite charge regions that you're looking at. All right, so it's going to set up a voltage difference. Notice that I'm combining all these concepts that we learned up to this point. All right, so there's going to be a voltage difference because the strength of the electric field times the separation distance is going to tell you about the amount of energy stored within this region. So the strength of the electric field times the separation distance is the voltage difference between these two. So which means that these charges, whenever you have a charge and place it in, whenever you place a wire here, each and every single charge is going to become energized. So what happens to that energy is going to turn into the kinetic energy of the charges. So the charges both start to move. It's every single concept that we discussed all of a sudden appears right here. So what's a current? It's the charges moving in the same direction. Which charges are moving in the same direction? Conduction and current. Normally they would be moving at random directions. So you kind of induce them to move in the same direction. So how do you do that? You have to set up two regions of opposite charges. That's it. So there's going to be an electric field. Electric field acting on the charges will induce a force, so they will accelerate. So that's one way of looking at it. So the electric field strength within this region is going to have energy stored in it. So when you drop charges into that region, charges will have potential energy. So potential energy is going to turn into the kinetic energy of these charges. And that's it. All right, so what drives charges? The summary statement is the voltage or potential difference does. Okay. So let's come up with a simple definition of current. So what is current? The current is the number of charges moving in the same direction. I is current, so this is number of charges moving in the same direction per second. That's what we will get to use. All right, so capital N is the total number of charges. All right, in my notes, I think I was using lowercase n. I switched the capital N because I'm going to use lowercase n for a different reason. I'm going to use it for electron charge density. All right, so these are the unit charges. In this case, we're dealing with the electrons. It doesn't matter, so it's going to be Coulomb. T is your time. It's going to be in terms of seconds. All right, so I is current. Current is going to be expressed in terms of A. A stands for amps. All right, so, or amperes, or amperes if you're French. All right, so current. All right, so this is number of charges per second is known as your current, so I'm going to keep modifying the expression. Number of charges per second, number of charges is the net charge, so we'll just change the expression a little bit more, so it's going to be net charge per second. All right, guys, number of charges is the same as net charge. All right, number of charges is the same as net charge. So Q is the net charge, which is the same as NE in this case. Net charge per second. So it's coulombs per second, which is the same as amps. So coulomb per second is the same as amps that we're looking at. All right, so the physics of it, one more time, let's just have a discussion. So the charge moving in the same direction is going to be current. All right, so it's the net charge, total number of charges per second moving in this direction, going across this cross-sectional area. Net charge per second is known as the current. What drives current is the fact that you set up a wire. You get a wire and set it up between two opposite charge regions. All right, so there's going to be an electric field acting on the charges, inducing a force causing an acceleration. Or a different way of doing it, the electric field strength times the separation distance is going to tell you about the amount of energy stored within that region. So when you place a net charge inside of it, the charge becomes energized. It's got potential energy that turns into kinetic energy. All right, instead of talking about it nonstop, 3-4 different ways, summary statement is what drives current is the voltage or potential difference. That's what we say. So the voltage or potential difference is the summary statement. So what drives current is the voltage or potential difference between two opposite charge regions. You don't need to even say that. You say, hey, what drives current is going to be voltage or potential difference. All right, so the current is going to be proportional to the voltage or potential difference. All right, so it means voltage or voltage difference. They mean the same thing. All right, so that's the summary statement. What drives current is potential difference. All right, so the official is the number of charges passing through a cross-section area per unit of time. That's something that kind of formal definition we'll go back and explore later. I just want to get a sense for what's going on. It's the number of charges moving in the same direction per second, net charge per second. What drives current is the voltage or potential difference. All right, so you need to set up two regions of opposite charges. And then obviously you've got a wire right here. And as soon as you contact the wire to these two opposite charged regions, what's going to happen? The negative charges will be repelled in the forward direction and attracted in the forward direction. That's your current, except this sort of current will last only a fraction of a second. It's like it's almost like a capacitor at this point. The charge will flow from a negative charge region to the positive charge region. That will be the end in reality. You will get a single zap through the wire, and then it will be completely depleted of these negative charges. So the question is, how do we keep replenishing the electrons to the negatively charged region so we have a continuous current? So at this point, this is no longer like a capacitor because you're able to keep the negatively charged region negatively charged continuously. And so the question is, how do we get to do that?